Hi, just I want to start talking about the second part of chapter 6, and we are still talking about how to calculate the work done on objects. And let's see here, this is a checkpoint where we are going to consider these two blocks. WA, the weight of A is 20 newtons and the weight of B is 12. Then the weight is given, not the mass. And they are going to move, like there is no friction in here for the first part. They move 75 centimeters. Find the total work done on each one. If there is no friction between the table and the 20 Newton block, and if the coefficient of static friction is 0.5 and the coefficient of kinetic friction is 0.325 between the table and the 20, we are going to calculate the work. Again, the steps are really draw free body diagrams for part A for mass A and mass B. Then we're gonna have like mass 1, it has the tension on it to the right. It has that normal NA upward. It has its weight MAG or WA downward. For the second mass, mass B, we have tension upward, MBG downward, and we have the acceleration downward. For mass A, we have the acceleration to the right. Of course, for mass A, I can say the work total is going to be the work done by the normal, the work done by the tension, and the work done by the weight. Okay, now in order for us to find what is the value of the tension, we need to solve for the Newton's second law equation so that we will calculate the tension. Okay, the tension here, if we will apply Newton's second law, horizontally, sigma F equals MAA, T equals MAA. I need also the equations from mass MB. I have T minus MBG equals, this should be negative MBA. That should be here negative. Okay. And then here I can substitute the value for T, MAA minus MBG to be MBA. And that is really the Newton's second law equation is going to be MBG should equals MA plus MB equals A after fixing the minus sign. And then A can be calculated as MB divided by MA plus MB times G. And then the acceleration was calculated as 3.675 meters per second square. Therefore, I can use that equation here, the tension, to calculate the what is really the the tension force. Here I divided by 9.8 because the weight was given and I need the mass. Now work total on mass MA is going to be the work done by NA plus the work done by MG plus the work done by the tension. And if you look here, you're going to find that the displacement is to the right, and I have 90 degrees between the normal and the motion, the direction of the motion. Also, the weight is 90 degrees, and therefore I will say both they're not gonna contribute to the work done. Then the work done is gonna be only the one with tension, and then it's gonna be the value 7.5 times 0.75 cosine 0, and that is the work done, which is 562 joules. For block B, we have the work total is going to be the work done by the tension plus the work done by mg, and you know the tension is upward, therefore cosine 180, and for the weight it is downward, then it's going to be 0, and then this is the work done by block B. This is the second part where we are going to assume again here that there is friction, and we can calculate like of course here I skipped some of the steps. Just here it's a Newton's second law problem where the weight of B minus Fk divided by Ma plus Mb should Ma plus Mb should equal the acceleration. Then I have calculated the new acceleration, and from that I can also again go to the equation for mass A and calculate the tension, which is which was calculated as 9.94 in newtons. Now the work total on object MA is going to be the work done by the tension plus the work done by the friction, and this is Ts cosine 0 plus Fks cosine 180, and that is really the total work done on mass 2.5 mass 1, sorry, mass A, 2.58 joules. For block or mass MB, the work total is going to be again WB, which is the weight of B minus tension times S. Okay, because of like we derived the equation before, and that is the work. Okay, then this is concluding this part. Now, this is repeated. Kinetic energy, it's the energy of motion. It is calculated as 1/2 mv squared. Like work, it is a scalar quantity. It depends only on the mass and speed. It has nothing to do with the direction, then it's a scalar. The change in the kinetic energy is K final minus K initial, and the unit used for kinetic energy is joules. Same mass, same speed, different directions of motion, same kinetic energy, has nothing to do with the direction. But when you look at the kinetic energy, it is increasing linearly with the mass of the object. Okay, then if you have a mass that is 2 kilograms, its kinetic energy is 100, and you know, moving with a certain speed. If I have that mass 4 moving with the same speed, its kinetic energy is going to be 200. But when we look at the speed, because it is a squared, then the situation is going to be different. If you have 2 meters per second, for example, mass that is moving with 200 having kinetic energy 200 joules, if we will double its speed, then the energy is going to be 4 times, 800. If we will triple, then the energy is going to be 9 times. Again here, this is the work energy theorem. Work total equals K2 minus K1, or the change in kinetic energy, or K final minus K initial. Now the work done by the external forces acting on the skater here is 0, but the skater's kinetic energy changes nevertheless. The explanation is that it's not adequate to represent the buoy as a single point mass. Now here it has a dimension. It has it's not a single point here. It is the buoy itself, the buoy himself here. It has a dimension, and forces are acting at different parts, and we call this is like a composite system. Now when we have the the force that we are dealing with is not constant, and we need to find what is really the work done, then I will say we are going to find what is really the area under the graph in order to get what is really the work. Sometimes it's going to be complicated, but sometimes it's going to be easy. And I will say, instead of calculating the area under the curve, what we can do is we can integrate. Here, this is calculation of approximate work done by the force over many segments of the bath, and we're trying here to make it, trying to, dissecting the graph into segments, different segments, where like rectangles, they are easy to find their, area, rectangles, and things that we need to know. Now, if I want to have exact, not an approximate, then the work done should be calculated as the integration of fx dx from x1 to x2. And this is, of course, the representing the area under the curve, of course, as we did in the lab. This is one example on forces that they are really not constant. For example, the spring force, or the force of a spring, which is we call it like the restoring force. It is according to Hooke's law, F equals minus kx. And when we graph it, it's going to be a straight line like this. If we wish to calculate what is really the work done, it's going to be the area under the curve, which is 1/2 times base times the height, and the base here is 1/2. The base here, it is x, and the height is kx. Then we can find that the work done by a spring or on a spring is going to be 1/2 kx squared. Now we can, of course, use as well the integration between 2 points x1 and x2, and we're going to conclude that the work done, it is 1/2 kx1 squared minus x 1/2 kx2 squared, and this is because we have initially a negative in the equation. Again, this is when it is very easy, rectangular area. You're going to say length times width is very easy. For the spring, it should be more like than this. It's going to be a triangle 1/2 kx squared. Now you are asked to design spring bumpers for the walls of a parking garage, a freely rolling 1,200 kilogram car moving at 0.65 meters per second is to compress the spring no more than 0.09 meter before stopping. What should be the spring constant of the spring? Assume that the spring has negligible mass. What we can do here is like drawing a diagram. This is my initial. The spring here was not compressed. The car is approaching with 0.65 meters per second. It is to the left, and therefore I give it like a negative because it is to the left. And then it will hit the spring and it will compress it a total distance of 0.09 0 meters, and of course it's going to be negative again because it is to the left. Now I can say here that the work done by the spring is going to be changing in kinetic energy, and the work done by the spring we said is going to be 1/2 kx1 squared minus 1/2 kx2 squared. Remember, finally is gonna stop, and therefore I will say we are going to have that negative 1/2 kx2 squared, and I'm sorry, no, the work done by the spring here, I'm not talking about stationary. I'm talking about, like, initially the spring was at the equilibrium point, which is x1 equals 0. Therefore this is 0, and this one, it is 1/2 k x2 squared. For the kinetic, it will finally stop, and initially it has a kinetic energy. We can make them equal here, and we will be able to find what is k. K can be calculated as the mass times the initial velocity squared divided by the x2 squared. And this is the value 6.310 to the 4 Newton per meter. Also, we can verify that we can use the work energy theorem for motion along a curve. And here we have an object or a particle that is moving along a curved path from point P1 to point P2, and that force is changing, and we can find the work done using the line integral f dot dl P1 to P2, and that can be simplified to be f cosine phi times dl, and it can be calculated. Another checkpoint here is consider the system shown in the diagram. The rope and the pulley have a negligible mass, and the pulley is frictionless. Initially, the 6 kilogram block is moving downward, and the 8 kilogram block is moving to the right, both with a speed of 0.9 meters per second. The blocks come to a rest after moving 2 meters. Use the work energy theorem to calculate the coefficient of kinetic friction between the 8 kilogram block and the tabletop. I need, of course, first to have the free body diagram. Okay. Normal, MBG, TFK. We know that they were moving with a speed which is a constant speed. Then for sure we're gonna have the force of friction here, and of course T should equals MAG since they are moving with constant velocity. Now K initial is going to be 1/2 mb v squared plus 1/2 MAV squared, and I can collect the terms. The K final is 0. Now the work total on the block A and block B can be calculated as the work done by friction plus the work done by the weight on A, which is the hanging mass. And I can say that the total work done on the system equals the total change in the kinetic energy. And then I will make these equal, and I can simplify and cross out the variables that I don't need, and find what is really mu K. Power is very important in many aspects because it is the rate at which the work is done, and the average power can be calculated as delta W over delta T, and the instantaneous power is going to be F times V, or the limit of that delta W over delta T. The unit for SI, the SI unit for power, it is joule per second or watts. There is another unit that we are familiar with, which is the horsepower, which is 746 watt. And actually here, Mr. James Watt, he was able to measure that using horses. Now, power is the rate of doing work, and it is work divided by time. And here time should be in seconds. Lifting a box here, work you do on the box to lift it in 5 seconds is going to be 20, and if it is 1 second is going to be 100 watt. Okay, this is the expression for the instantaneous. P equals the scalar product of F dot V, which is FV cosine theta. This concludes this chapter, and I will meet with you to work on chapter 7. Thank you. Have a great day.